Welcome you all in my next lecture. So, this lecture I will talk about partial derivatives. Of course, the notion of partial derivatives I already discussed in my last lecture. So, this lecture I will talk about more about partial derivatives in a sense that there is a concept called higher order partial derivatives that I will talk about that, along with the notions of directional derivative and total derivative. Then you will have chain rule and so on and so forth. So that is the primary plan. So, I will start with a few things about partial derivatives and then I will move to what is called directional derivative and then I will talk about total derivative. Okay. So the notion of partial derivatives for a function f whose range is R and domain in Rn, that means real valued functions with vector variable, sometimes this is called scalar field. For this kind of functions, I introduce the notions of partial derivatives. That means, if I have a functions f from Rn to R, so Rn has how many variables independent? N variables x1, x2, xn, or Rn has an orthonormal basis consisting of n linearly independent vectors. So, therefore, I have n many directions, and for that directions corresponding the notions of partial derivative I have discussed. So, this is again I already discussed in my last lecture that if I like sum product of a chain rule kind of thing. So, that means what? That means if I have two functions like f and g, both are defined from some open set Rn to R, then if the partial derivative of f with respect to xi variables at x0 exists and the partial derivative of g with respect to xi variable at x0 is exists, then what can I say about the sum, what can I say about the product. So, these are the things again like in the differentiation in the real single variable case, the similar kind of things is true. That means, the partial derivative of f plus g with respect to ith variable at x0 it split it up. That means, partial derivative of f with respect to xi variable at x0 plus partial derivative of g with respect to xi variable at x0. Similarly, scalar multiplications, you can take out the lambda from outside. That means, partial derivative of lambda f with respect to xi variable at x0 is exactly equal to lambda times partial derivative of f with respect to xi at x0. Dot product. So, if I have two, since f and g partial derivative with respect to xi variable at x0 exists, so what can I say about the product functions f g? So, again the kind of partial derivative of the product functions f g with respect to xi variable at x0 exists, and you can write in terms of the partial derivative of f with respect to xi and partial derivative of g with respect to xi. So, this is the formula. That means, partial derivative of f with respect to xi at x0 times g x0 plus f of x0 times partial derivative of g with respect to xi at x0. And the last one is a chain or composition rule. That means, if I have a functions, real valued functions of real variable, suppose it is differentiable at the point f of x0, then if h composed f makes sense, then I can talk about the existence, because what will happen, h composed f is again a functions from where to where, it is a functions from S subset of Rn to R. So, therefore, I can talk about the partial derivatives of h composed f with respect to xi variable, and this is called compositions or chain rule. That means, and you can write it that partial derivative of the composition functions h composed f with respect to xi variable at x0 is nothing but the derivative of h at f of x0, which is exist, I already in the hypothesis, times the partial derivative of f with respect to xi variable at x0. So, this is chain rule. So, more or less like whatever the properties for the real valued functions of real variable derivative is true, some of the things are true, similar sort of things are true in the case of partial derivatives. Okay, as I said, so once I have partial derivatives, then I can talk about partial derivatives of higher order. Before defining what do I mean by partial derivatives of higher order, let me see some examples. Okay, so let f is a functions from R2 to R. So, this is the different kind of functions, it is kind of polynomial in x and y, that means x4y plus yqx. Okay. So, now if I calculate the partial derivative of f with respect to x, of course, this function is very nice function. So, one can easily see that the partial derivative with respect to x and with respect to y always exist. And what will be the partial derivative with respect to x at the point x y? As I said, when I am talking about or going to calculate the partial derivative of f with respect to x, you just keep the variable y as fixed variable. That means, think about it as a function of R to R and do the derivative that you know in the single variable case. So, that means, here you just keep y fixed, think about it as a functions from R to R and just do the derivative with respect to x. So, if you do that, then it becomes 4x cube y plus y cube, and similarly for the del f del y you can do that. So, again, so keeping x variable fixed, just kind of think about the function as a function from r to r and do the derivative with respect to y, that is it. So, that is the del f del y is nothing but x4 plus 3y square x. So, now the point I am making here that now this first order partial derivatives are again a functions from r to r. So, that means this is, what is this? This is nothing but, what is this? This is del f del x, okay, del f del x at the point x y, which is same as 4 x cube y plus y cube. So, that means del f del x itself. So, del f del x itself a functions from r2 to r. Since it is a functions of r to r, again I can think about the partial derivative of del f del x with respect to x variable and with respect to y variable. Similarly, del f del y is also a functions from r2 to r. Okay. I can also think about, since it is a functions from r2 to r, so I can think about the partial derivatives of del f del y with respect to x variable and with respect to y variable, and that is exactly I have written. Okay. So, now the first order partial derivatives are again functions from r to r. Since it is a functions from r to r, again we can do partial differentiation with respect to the variables x and y, and if you can calculate it, right. So, del f del x, you know, this is the functions del f del x at x y is nothing but 4 x cube y plus y cube. So, you just make the partial derivatives of del f del x with respect to x variable, again do the same thing, put y as a fixed variable and do the differentiations. So, that means this is nothing but del del x of these functions 4 x cube y plus y cube, and this is nothing but 12 x square y. It's keeping y variable fixed. If I do the differentiation with respect to x, this will contribute nothing because it is a constant, this is 0, only this part will contribute. So, that means it should be 4 x cube, what is the derivative? That means 12 x square, and y is constant, keep y. So, therefore, this is nothing but 12 x square y, and this is, I can write it in terms of notation del 2f del x square. Similarly, I can take the partial derivative of this function with respect to y variable, do the same things, you will end up with this one. So, this is says that del 2f del y del x. Look, this is the notations actually. So, the right hand side notations del 2f del y del x, that means the first one. So, right hand side del x, that means you just do the partial derivative of f with respect to x variable first and then do the y variable. So, that is the kind of notations. Similarly, again as I said, del f del y also I can, it is a functions from r to r. So, therefore, I can kind of compute the partial derivative of del f del y with respect to x variable and with respect to y variable. If you calculate the x variable, it will be like this one, I am denoting as del 2f del x del y, and if I have del y, this is del 2f del y square. So, only part is you should remember that whenever I am using this kind of notations, that means what I am doing is that the right part, that means in the denominator you have del y del x or del x del y. So, if it is del x del y, that means first you do the derivative with respect to y variable first and then x. Similarly, here with respect to x first and then y of f. So, that is how. So, this is the notation, this is called partial derivatives of higher order. So, that means if I have a functions f from say r to r, which is nice, then del f del x del f del y I can think about is a functions from r to r once again, and therefore, I can talk about the partial derivative of that functions, that is del f del x and del f del y with respect to x and y variable respectively, and that will give you the partial derivatives of higher order. So, this is for r to r. So, what will happen for r n to r? So, r n to r as I have written here. So, notations for partial derivatives of higher order. So, if I have a functions f from some open set a subset of Rn to R, then this is the notations I am writing. What I am writing? Look, del 2f del xj del xi. So, that means the notation stands for, that means first what you do, you take the partial derivative with respect to xi variable first, and then think about this del f del xi as a functions from again Rn to R, then take the partial derivative with respect to xj variable. That is first xi then xj. So, that is the kind of notations. So, and that is again I am writing. So, this is the notations, okay. Then I am writing this is dij. So, again you say that okay, first how the notations from the notations I can think about that which variable I should do the partial derivative first. If I use this dij notations, the notations I which is near to d. So, with respect to that we have to do the partial derivative of f first. That means in d suffix ij, which one is most closer to d, which is I variable. That means you should do the first partial derivative of f with respect to xi variable and then do the partial derivative with respect to jth variable of the functions del f del xi. That's how the notations. So similarly, f xi xj, again say xi is close to f, so that means in notations xi is near to f. That means what you do first, you do the partial derivative of f with respect to xi variable, then think about the functions del f del xi as a functions from Rn to R, and then do the partial derivatives of del f del xi with respect to x variable. So this is a derivation del of ijf del xijf. Similarly, if I say suppose del q, that means with respect to del xi, del xj, del xk. So this is the notations. So this notation means, that means I am first doing the partial derivative of f with respect to xi variable, that means del f del xi. Think about del f del xi as a functions from Rn to R, then do the partial derivative with respect to xj variable. So that means you consider del 2f del xi del xj, again it is a functions from Rn to R. Then you do the partial derivative of this function, that means del 2f del xj del xi with respect to del xk variable. So that's I am denoting as del qf del xk del xj del xi, which is exactly this one. Then first do the partial derivative with respect to xi variable, think about this as a function from Rn to R, then perform the partial derivative with respect to xj variable, think about this as a function from Rn to R, and then perform the derivative with respect to x variable. So again this is the notation d suffix ijk. Again as I said, that means I is nearer to d, that means you have to do first partial derivative with respect to xi variable of f, then do the partial derivative with respect to xj variable of the function del f del xi, and then do the partial derivative with respect to x variable of the functions del 2f del xj del xi, and this is the notations, and so on. So that's how it goes. So again I have written here what I said in the notations d I j k if the index I which is close to d is first, then next index j, and so on. In the notations f of xi xj xk, the variable xi which is close to f, as I said already, is the first, then next to the variable xj, and so on. So that's how from the notations you can guess with respect to which variable I have to do first partial derivative of the given functions, and think about that functions again from R to R, and then which variable I should do the partial derivative next. So that's how the notations I already explained. What is mixed partial derivative? Mixed partial derivative is, I say that dij dgi, that means you have to just do the partial derivative of the given function with respect to xi variable, and then if you do the partial derivative with respect to the other variable xj different from I, then I will say that is a mixed partial derivative. That means you are taking the partial derivative with respect to x, and then we should take the partial derivative with respect to y variable. Okay, that's I not equal to j. Okay, it's called the mixed partial derivatives. Later on, when I will talk about the total derivative of a given functions from Rn to Rm, then you will see there are some properties, kind of properties in a sense, that means I can talk about the total derivative or the differentiability of the functions Rn to Rm in terms of partial derivatives or mixed partial derivatives. There are some sufficient conditions. So that time you might need those kind of notations for higher order partial derivatives or mixed partial derivatives. Okay, so that's I think little bit about partial derivatives. That means what is the kind of, if I put it together all the informations, and if I say that okay, start with the functions f from Rn to R, okay, from some open subset S subset of Rn to R, then what I am doing is that I am just keeping, like suppose if I have a function from Rn to R, what I am doing is that I am keeping, suppose if I want to do partial derivative with respect to xi variable, that means except the variable xi, so other variable I am keeping fixed. Okay, I am thinking my functions as a functions from R to R and perform the differentiation with respect to that variable. That's exactly I am doing. So that means I am doing nothing but the derivative that you are familiar with the real variable case, so single variable case, when R to R. I am keeping all other variable fixed except that ith or jth variable with respect to which I am trying to perform the derivative, and that I am saying that partial derivatives. In other words, if I have a Rn, you have n many vectors independent, or n axes are there independent. So those with respect to those x for R2, that means you have x axis, y axis, okay, coordinate axis, or it has orthonormal basis consisting of two vectors. So with respect to x, with respect to y, I can talk about the derivative of my given functions f from R2 to R, keeping one variable fixed. I am thinking about as a function of R to R and perform the derivative that you know. So that's for R2 case, and Rn case you just do the similar extension, that means keeping all the variable fixed except the variable you want to do the derivative. So, this is all about the partial derivatives. That means, if I have R2 or Rn, if I have the coordinate axis, that means with respect to, I should say, the EI means, that means all coordinates 0 and ith coordinates is 1. So, therefore, with respect to that, I am performing the derivative in that way. So, now there is another concept or another notion that is called the directional derivative. What is directional derivative? So, you will see when I will talk about the definition of directional derivative, if I fix the directions like the coordinate axis, then you will end up with the partial derivative, whatever I have just discussed. So, actually, in other words, what I am trying to do is that, actually what I am doing, I have a functions from Rn to R, right. So, what I am doing is that keeping one direction fixed means, even if I am in R2, my function is from R2 to R, one dimension is fixed means I am thinking about as a functions on R. So, like in the coordinate axis, suppose I have a functions from R2 to R, right. Once I fix the x axis, that means I am in real line, right. X axis means one dimension, right. So, this is one dimension. So, that means I am in the real line. So, even though my function is given from R2 to R, but I am thinking that functions, because I am fixing one direction, right. So, that means other direction is fixed. So, that means I am thinking my functions from R to R and then perform the derivative that you know. So, here also I am doing the similar kind of things. So, directional derivative means what? Suppose if I have a functions from R2 to R, what I am doing, if I have a functions from R2 to R, so partial derivative means I am doing the derivative either in x axis direction or in the y axis direction, means coordinate axis directions. Directional derivative, what I will do, I do not care that only these two directions, I say that okay, take these directions passing through origin, suppose. And what can I say about the derivative with respect to this direction, suppose this is my direction. So, once I fix the one directions, that means actually I am coming back to the R case, I mean real line. So, even if I am in R2, once I am fixing one direction, that means I am in R, and if do the derivative from R to R function. So, that exactly I am doing. So, when I will have the definition, I will explain the definition, then we will see once I fix the direction like coordinate axis direction, it boils down to the concept of partial derivatives. Okay, what is the definitions? So, let f be a functions S subset of Rn to R, where S is an open set. Let x naught in S, let u be a unit vector in Rn. If I have a unit vector in Rn, then corresponding like line I can talk about the directions, or line I can talk about which is like scalar multiple of u, that will be a line passing through origin. Okay. So, once I have the unit vector, that will give a direction, or that will give a line passing through the origin, and I want to talk about the derivative of my function with respect to that directions. Okay. Earlier you will have only coordinate axis direction, now here you do not have any restrictions on the directions. Take any vector, unit vector, consider the line passing through that point u, this is the directions, this is a line passing through the origin containing the vector u, and you talk about the differentiability with respect to that directions. Okay. You will see that same definition will be there, except the earlier one I will have only two directions like e1, which is nothing but 1, 0 and e2 is 0, 1. Now, here you will have any unit vector, will give you directions and perform the derivative like partial derivative, whatever the definition of derivative I have given, do the same thing. So, it is look at the definitions. So, the directional derivative of f at the point x naught in the direction u is defined by, okay. So, this is the notations, that means d suffix u of f, that means d stands for directional derivative of f of the functions, suffix u means in the direction u, and at x naught. What is the definitions? Similar kind of definitions you have already seen in the partial derivative case. What I am doing is that take the limit of this quotient. What is this quotient? Okay. So, limit t approaches to 0, f of x naught plus t u minus f of x naught divided by t. So, that means what I am doing is that x naught is fixed, u is fixed. So, what I am doing is that I am considering t u as t varies, that means I am in a line passing through the origin and containing the vector u. So, that means I am in one directions, and then the direction given by the vector u. And I would like to see the changes of the points on this direction itself. Okay. So, that means f of x naught plus t u minus f of x naught divided by t. If this limit exists, then I will say that directional derivative of f in the direction u at the point x naught exists, provided the limit exists. I have written, so du f at x naught, it is nothing but the rate of change of f at x naught in the direction u. That is very important, because I am keeping this vector fixed in the direction u, I am talking about the changes. So, this is the notations. Okay. So, du f x. Now, as I said, you just fix the direction earlier. Suppose you may say that, okay sir, if I talk about like if I fix the directions, say coordinate axis direction, can I get back to my partial derivative definition? Answer is yes. Look, so if I fixed u is equal to ei, because I am in Rn, so it will have a n vectors, n orthonormal consisting of, you have an orthonormal basis consisting of n vectors, and that, as I already said, this is nothing but E1, E2, En. Okay. What is Ei? Ei is nothing but 0, 0, 0, 1 at the ith place. Okay. So that will be a orthonormal vectors. Okay. So now this is called the coordinate axis directions. Now if I just replace u by this vector Ei, so that means d suffix Ei of f at x naught, then what will happen? So this by definition is nothing but limit t approaches to 0, f of x naught plus t Ei minus f of x naught divided by t. And that is nothing but, if you remember, that is nothing but the partial derivative of f with respect to xi variable, because I am in the coordinate axis direction xi at the point x naught. So therefore, if I put u is equal to ui, that means I have the definitions of partial derivative of f with respect to xi variable at x naught, and that I already denoted as di of f at x naught. So therefore, directional derivative is very general. That means I am trying to kind of, once I fix the directions, okay, I am thinking about the changes of the point x naught in that directions. In other words, once I fix the direction, that means I am fixed a line. Even if my functions is defined from R2 to R, I am thinking, since I am talking about the changes only in the line, I am thinking about my functions from R to R. Okay, and then I am performing the derivative like you know the derivative from R to R functions. That exactly I am doing. So if you just do any directions u with the norm of u is equal to 1, that is called the directional derivative. If I choose u is equal to coordinate axis direction, it boils down to the concept of partial derivatives. So therefore, if directional derivative exists in all directions at some point, then I immediately say that my partial derivative exists with respect to coordinate variable at that point. Okay, so that's the directional concept of directional derivative. And then, like in my last lecture, I discussed that whether the existence of partial derivatives will imply the continuity of f, or the continuity of f implies the existence of partial derivative. These are the things you may ask in this setting as well, whether the existence of directional derivative have anything to do with the continuity of the functions. So let's see. Okay, before that, I think better to calculate some examples. Okay, for example, I have a nice function f of xy is equal to xy, and these are continuous functions, right? So now the questions I have given is that find the directional derivative of f at the point x naught is equal to 1 comma t in these directions. You just apply the definition, that's it. So what is the definition? Suppose if I, so that means I want to find, that means d u f, that means directional derivative of f in the direction u at the point x naught. X naught means 1 comma 2. I am writing x naught here. What is the definition? So this is limit t approaches to 0. Okay. Then what will happen? F of x naught plus t u, okay, minus f of x naught divided by t. That's limit you have to calculate. And what is this? This is limit t approaches to 0, f of x naught is 1 comma 2 is given. So 1 comma 2 plus u is given root 3 by 2 comma half. So that means t times u. So that means this is nothing but t times root 3 by 2 comma half, okay, minus f of 1 comma 2 divided by t. What is this? This is limit t approaches to 0, okay, f. Now you just add the coordinates, because you hit t in the component wise and add it. So what will happen? This is 1 plus t times root 3 by 2, okay, then comma 2 plus t times half minus f of half divided by t. That's limit you have to find. What is this? This is limit t approaches to 0. Okay, so but the function is given f of x y is equal to x times y. So what will happen? This is nothing but 1 plus t times root 3 by 2, okay, times 2 plus t by 2 minus 2 divided by t. Do the algebra. What will happen? This is limit t approaches to 0. What will happen? This is 2 plus t by 2 plus t root 3 minus, or plus, sorry, this should be root 3 by 4 times t square minus 2, right? Do the algebra, that is it. 2 get cancelled. Then what will happen? This is limit t approaches to 0. Now tt, that means this will give you half first one, second one give you root 3, and third one give you what? So root 3 by 4 times t. And if I take the limit, what will happen? First one it will be as it is because it is independent of t. So that means this should be half plus root 3. That's the value. It's very easy. So like you just follow the definitions. You just use the definitions and do the calculations, you will be able to do that. A very nice function. So what I have seen is that, so I have a point x naught fixed, I have a directions, and I can easily calculate the direction derivative, the definitions I have given. This is one example, but my function is very nice, it is a continuous function. Okay. Okay. Now this is another example. As I said, okay, look, what I said is that du f 0, that means directional derivative of f in the directions u at the point 0 exist for all u, that means whatever directions I am considering. So that means I have the existence of directional derivative in any directions at the point 0 exist, however, my function is not continuous. Okay, this is example. So that means the existence of directional derivative at the point in any directions will not imply the function is continuous. So that's the example. So this kind of functions you might have seen in my earlier lectures. This is not continuous, you can easily see because I have already written the function is not continuous because you choose the path x is equal to ky square. Okay. So this kind of path if you will choose, and if you come to the origin, then you will see it values from different values of k. And so therefore the limit does not exist, and here therefore the function is not continuous at the point 0, 0. So that is easy because by looking at the functions you can easily get the corresponding path. So that means if I want to talk about the continuity at the point 0, 0, first I have to see whether the limit of this function at the point 0, 0 exists or not. Answer is that limit doesn't exist. If I come through the path x is equal to ky square, it will give you the value 1 by I think k square by so it should be give you the value some functions of k, and that functions of k varies for different values of k, that's it. So therefore limit does not exist, and therefore my function is not continuous. However, if I have the function, if I want to talk about the existence of directional derivatives at the point 0, 0 in any directions, it is exist. Okay, and I didn't calculate it, but I have said that if a is non-zero, this is b square by a, and if a is equal to 0, this the value will be 0. Just so for example, if I just calculate it at the point 0, 0, so what is the definitions? So this should be limit t approaches to 0, okay, f of, so I am talking about the directional derivatives at the point 0, 0, so that means this is 0, 0 plus t times u means ab, okay, minus f of 0, 0 divided by t. So that's kind of limit you have to calculate whether it exists or not. Okay, and this is what? This is limit t approaches to 0. Okay, 0, 0 plus t times a comma b. What is this vector? This is nothing but f of t a comma t b, and f 0, 0. What is the value? This is 0 divided by t. And what is this? This is limit t approaches to 0, and what is the value of f of t a comma t b? Okay, so keeping that mind that a is non-zero, that means you just calculate the value. This should be what? This should be t a times t b square divided by t a square plus t b 4, and then you have 1 t. Okay, then what will be the limit? So limit t approaches to 0. That means what will, how many t's? So that means t square, that means tq will come out, you will have ab square divided by, you have t square a square plus t4 b4 times 1 by t. What is this? This is limit t approaches to 0. Now 1 t get cancelled, that means this should be power 2, and 1 t square will come out from the denominator. So what will remain? So this should be a b square divided by a square plus t square b4. And what will be the limit? So limit, that means this part will go to 0, so that means this should be b square by a, and that exactly I have written. That is for a is non-zero. If you put a is equal to 0, again just perform the same definitions, you will be able to calculate the directional derivative of f in the directions u at the point 0 is 0. So therefore, in this example what I observed is that even though the directional derivative of f in the direction u at the point 0, 0 exists, my function is not continuous. Okay, another example I would like to talk about, again similar sort of examples. Okay, what examples? So the partial derivative exists, as I said, is okay, that question you can ask. So like as I said, that if the directional derivative of a functions on all directions at the point exists, that will automatically imply the existence of partial derivatives. What will happen? The converse. I mean, existence of partial derivatives, can I say that directional derivative exists at that point in all directions? So this kind of examples, this example says that it is not the case. That means partial derivative exists, but directional derivative along other direction do not exist. So look at these functions, f of xy is equal to xy divided by x square plus y square, this sort of functions you already seen in my lectures. So, first you calculate that the partial derivative of f with respect to, since it is a function from R2 to R. So, that means partial derivative with respect to x variable and with partial derivative of f with respect to y variable, that I am denoting as d1f at 0 0, d2f at 0 0, that is exist. You can calculate it by hand using the first principle definitions, you will be able to show that this is equal to 0. However, if I take any vector u a b, an unit vector where a is non-zero, b is non-zero, this directional derivative does not exist. If you perform it, we will say that that does not exist. In that case, we will say that limit does not exist, because by just look at the functions, if you calculate the formula, then what will happen? This kind of limit you have to calculate. Limit t approaches to 0, f of, at the point 0 0 I am talking about, so this is 0 0 plus t times a comma b minus f of 0 0 divided by t, and what it will give you, t approaches to 0. So, this should be what? F of t a comma t b, okay, and f 0 0 is 0. So, therefore, this is divided by t, and what is this? This is limit t approaches to 0, f of t a t b, what is this? This is t square, okay. So, t square a b divided by okay. So, yeah, so t a t b, so t square will come out, so t square a square plus t square b square, okay. So, that df does not exist, okay. So, be an unit vector non-zero, there is something wrong, okay. So, I have a vector u b unit vector, I just show that du f f 0, so that is perfectly all right. So, f 0 0 is 0, so it is non-zero, so this limit t a t b, okay. Maybe I think there is something there it exists actually. So, maybe I think I will come back in the next lecture. So, whether I am kind of saying the right part or not, whether this example, that whether I am claiming that partial derivative exists, but the directional derivative along other direction do not exist. Existence of partial derivative is quite clear from the definitions. However, whether the directional derivative along other direction do not exist, that I have to make sure. Okay, maybe in the next lecture I will talk about, in fact I will start from this fact. So, in other words, what I am trying to say is that existence of partial derivative will not imply existence of directional derivative. Of course, existence of directional derivative in any directions will give you the existence of partial derivatives. So, the converse part is not true, and that is, I think I am trying to give you one example to justify you. Look, this is the example where you have the existence of partial derivative, however, you do not have the existence of directional derivative in other directions. So, that is the kind of plan, that is the kind of the example I want. Maybe I think next lecture I will start with that. Okay, thank you.